So this is the last example that we stopped at last time. We didn't finish this example. So in section 2.2, we'd introduced the derivative as a function. And here we were asked, and then we talked about higher derivatives as well. So we talked about the second derivative is defined to be the derivative of the first derivative, and so on and so forth. So this was an example where we were asked to find the second derivative. So in a previous example, we had shown that the derivative of the positive square root of x is, and we use the limit definition, is 1 over 2 root x. And so now to find the second derivative, we're going to do a limit definition on the first derivative. And folks, so in class, this will probably be the last time we do a derivative this way, thank goodness. So in section 2.3, we'll get our shortcut rules. And then finally, we don't have to do the limit definition anymore. So, in general, I would always say, just follow the instructions. If the instructions say to use the limit definition, then use the limit definition. Otherwise, I would use the shortcut rules, which we'll talk about shortly. So here's the usual definition. So f prime of x plus h. So remember here, f looks like this. So f prime of x plus h would be 1 over 2 root x plus h, and then minus 1 over 2 root x. And now when you try to apply this limit, you get 0 over 0. So when you let h equal to 0, these two terms cancel out and become 0, and in the denominator, h becomes 0. So when you try to apply the limit, we get 0 over 0. Looking at it, what we notice is that these two fractions can be combined into a single fraction. So I'm going to multiply the first fraction by root x over root x. So in the numerator, I get a root x. I'm going to multiply the second fraction by root x plus h. They both already have a 2 in there. So I just multiply the second fraction by root x plus h over a root x plus h. In the numerator, we get a root x plus h. So after I combine the fractions, it looks like this. So let me get rid of this here. So after you combine the fractions, it just looks like root x minus root x plus h over 2 times root x plus h times root x. And so here, again, if you try to apply the limit, if you send h to 0, or sorry, I guess I did it up here, I got confused. It's right here. There's that next step. You combine the fractions. And now when you send h to 0, again, we get 0 over 0. So now from the form, and this was on the exam as well, basically this form here in the numerator, that's a tip-off to us to multiply top and bottom by the conjugate. And so that's what I do here in the next step. Here, as you know, the conjugate of root x minus root x plus h is root x plus root x plus h, and I'm multiplying top and bottom. So in the numerator, we get x minus quantity x plus h. Okay, so now look what happens. I did it all in one step, so this might look a little confusing. So first, this minus sign will distribute to both terms. And then this x will cancel with this x. So then I'll have a minus h on top, but there's a h out in front. So now this minus h will cancel with the h down here. I'm just going to be left with a minus 1. Just the minus 1 will be left on top when you cancel everything. So first cancel the x's, then you have a minus h on top, and cancel the h with the h that's right here in the denominator. So that becomes a minus 1. And so I purposely skipped a step there because I want you to take a second look at that and make sure you understand the algebra. And so now we apply the limit. Right here, I replace this h with 0, this h with 0. This just becomes root x, 2 root x, which is right here. And here we have root x plus root x. So in the parentheses, I get 2 root x. And so now I'm just multiplying all this out. 2 times 2 is 4. root x multiplied to itself 3 times is x raised to the 3/2. So there's my second derivative with the minus sign here from the numerator. So yeah, in class we will never do a derivative like this again, thank goodness. And so here's the full chain of derivatives. The derivative of positive square root of x is 1 over 2 square root of x, and the derivative of that is negative 1 over 4x to the 3/2. So we'll get a shortcut rule for exactly all of this that I'll show you in a couple of minutes here. So this is the last example in section 2.2. It's an important one. So it's not difficult, but it's one that our brain has to get used to. So if you haven't seen it before. So in this problem, notice we're given the graph of the derivative of f of x. So I have the graph of the derivative. So, and here we're asked to find, based on that sketch, the actual graph of f of x. And so now I want to find the graph of the original function f of x. So it's not difficult, but we just kind of requires sort of to shift the way we think a little bit. Like for example, when I look at this graph, I know, this part here, everything, this section here, everything to the left of this x-intercept point here, everything to the left of that x-intercept point. You see here the derivative is negative. The derivative, the graph of the derivative is literally below the x-axis, so the graph is negative. That means the original function in this section is going to decrease if the graph is negative. And now if you look at this section here, in between the, oops, let me change colors. If you look at this section here, from this x-intercept to this next intercept that's right here. So here's the other x-intercept. There's an x-intercept right here. And there's one right here. I didn't really draw it well last time. Right here. In this blue section, between the two x-intercepts, look, the graph of the derivative is above the x-axis. The graph, that is to say the derivative is positive. If the derivative is positive, it needs to increase in this section. So in this section, the graph of f of x between the x-intercept here, which is a prime, and the x-intercept here, b prime, the graph needs to be going up. And so already we start to get a sense of the graph, that it's going to go down, it's going to have a low point, and then come back up. And now again in this section, where the derivative is below the x-axis, that's where the derivative is negative, that's where the function is decreasing. So now I expect, so look, it decreased, it hit a low point, it went up, it hit a high point, and now it's starting to decrease again. Remember, wherever the derivative goes through the x-axis, that means the derivative is 0. We have a horizontal tangent wherever the graph of the derivative goes through the x-axis. So this final section, again, the derivative is above the x-axis. So now I expect the graph here to increase. And so we want to just kind of correlate these things. So if you look at the graph here, it starts out, as we said, by decreasing. Then we have this horizontal tangent right here that corresponds to where the graph of the derivative goes through the x-axis. It's right here. We have this horizontal tangent. And then the graph starts increasing. So again, for this section here, it's increasing. And then we get another horizontal tangent. Right here where the graph crosses the x-axis, we have a second horizontal tangent. And now the graph of the derivative is below the x-axis, so the function is decreasing. And at the x-intercept of the derivative, we have horizontal asymptote, and then finally the function starts increasing again as per, the graph of the derivative. The graph of the derivative is above the x-axis, so that means the function should start increasing again. Now, one thing to keep in mind is the actual positioning of this curve is unknown. So a curve that looks like this, if I have the same curve but shifted up, the derivative will look the same. If I had the same curve, same shape, but shifted down, the derivative only gives us shape information. It doesn't tell us where it's actually located on the plane. So using the derivative and determining where the derivative is positive and negative, we can sketch, the graph of the function. So it's important that you be able to go from the graph of the derivative to the original function, as well as from the original function to the graph of the derivative. So for example, here, I would say, oh, in this section, the function is decreasing, so the graph of the derivative has to be below the x-axis. And then where it has a horizontal asymptote, that's where it crosses the x-axis. And then where it's increasing, that's where the graph will be above the x-axis. So on and so forth. So it's not difficult, but you kind of have to do a little kind of mind shift, We're not used to interpreting things graphically and visually like this, and that's part of what we're trying to accomplish in calculus and math in general. So yeah, when you're looking at the derivative here, first think about wherever it crosses the x-axis, that's where you have a horizontal tangent. Wherever it's below the x-axis, that's where the original function is decreasing. Wherever it's above the x-axis, that's where the original function is increasing. So yeah, something to practice, and it's good because, like I said, it's a little bit different. We typically don't do this type of visual analysis. So this ends section 2.2, and without further ado, I want to switch right to section 2.3 because that's what we're supposed to cover today. So in section 2.3, we finally get to rid ourselves of the limit definition of the derivative. We introduce shortcut rules. So remember, what we're shortcutting here is, instead of using this limit definition to find the derivative, we'll now have a series of rules depending on what the situation is. For example, if you're taking the derivative of a constant, that's always 0, and I'll give you some more rules. So here, I also wanted to review some notation here. So here, this is the derivative of f, but this is more declaring intent, that here's the original function f, and I'm about to take a derivative. I haven't actually taken the derivative. And then f prime of x, this is the derivative. We've either used the derivative rule or we use the limit definition and we got a function out. Another way to write f prime of x using Leibniz notation would be df dx. D for the derivative of f with respect to x. So yeah, we don't need to use this limit definition anymore in section 2.3 because we're now given the following differentiation formulas, which we should memorize. That's the thing with shortcuts. If we're going to learn a shortcut, typically shortcuts are about just memorizing them. So now we should memorize these, and these rules should be at our fingertips. So the first rule, and the most basic derivative rule, is that the derivative of a constant is 0. If you interpret the derivative as a slope, remember the slope of the constant function is 0. Or we can use the definition. We can use this definition. In this case, f of x would be the constant c. So here, f of x plus h would just be c, minus f of x would just be c, and here I'd have 0 over h, and so the limit would just be 0. And so the derivative of a constant for any constant is 0. The next rule is very important. It's called the power rule. It's called the power rule for differentiation. We will also have a power rule for integrals, okay? But this is the power rule for differentiation. So it's for a polynomial of the form, we've got a variable x raised to a number, say n. And I want you to contrast this. It's not an issue now, but a little bit later in life, we will look at a function of this form where it's a number n raised to a variable x, and the derivative rules for these two different functions are drastically different, okay? So that's why I'm already trying to emphasize that here we have a variable in the base and a number in the numerator. So the differentiation rule is, so the derivative of x to the n, so the rule says bring down, so this equals, so the rule says bring down the n. So I bring the exponent down and then copy the base and then subtract 1 from the original exponent. So it's x to the n minus 1. So, you know, now it's incumbent upon us to have this procedure in place where we go, oh, this is a derivative problem. And the thing I'm trying to take derivative, oh, it's a variable raised to a number. Aha, I need to use the power rule. So, you know, that's kind of now part of the procedure that we recognize we're doing a derivative and that it's a variable raised to a number, so it's a type of polynomial. And so we use the so-called power rule. The next the next thing isn't a differentiation formula as much as it is a property of the derivative. So this says the derivative of a constant times a function is equal to the constant times the derivative of the function. So here it's the order of operation. Here they're multiplying the constant to the function first and then taking the derivative second. On the right-hand side, we've taken the derivative of the function first and then multiplied by the constant. So this says they're the same. You can multiply by the function, you can multiply the function by a constant first and then take the derivative, or you can differentiate the function first and then multiply by a constant. You know, they're equivalent. The way we usually view this is that you can quote unquote pull the constant out of the derivative. Of course, we're not physically moving anything, but that's just the way we think about it. So here, if you have c times f of x prime, I can pull the constant out. And a similar thing with the sum or difference, the derivative of a sum is equal to the sum of the derivatives. Similarly, the derivative of the difference is equal to the difference of the derivatives. Again, it's when we do things. So here we're first adding or subtracting, then we're taking a derivative. On the other side, we're doing the derivative first, and then we're doing the addition or subtraction. And again, the informal way we think about this is that we can quote unquote distribute the derivative to each term, you know, across sums and differences. Again, we're not, you know, physically moving anything, but that's just how we think about it. You can pull constants out and you can distribute the derivative across sums or differences, not products, sums or differences, not quotients. Here, this last one, this is the legitimate differentiation formula too, in fact. The derivative of sine of x is equal to cosine of x. I'll prove that one in a second. And the derivative of cosine of x equals negative sine of x. So as I said, these are all rules we should memorize and be careful here. The derivative of cosine has a minus in front of it. The derivative of sine doesn't. Derivative of sine is just cosine, but derivative of cosine is negative sine. So let's practice doing a derivative or two. So here we're asked to find the derivative of x to the fifth plus 6x minus 8 over the square root of x. We're asked to find the first derivative, f prime of x, and the second derivative, f double prime of x. So the first thing we should notice is we don't have a rule yet for how to take the derivative of a quotient. Think about this. This is a function on top divided by a function on the bottom. On the previous page, we only got rules for something that looked like this, x to the n, or cosine, or sine, or sum or difference of functions that we already know the derivative of. Not a quotient, sum or difference. So here, the trick here is to rewrite this. Here is to realize, you know, we can use algebra, and this is a general comment I want to make, that anytime in the denominator you have a single term by itself, one strategy to keep in mind is breaking up the fraction. And so here I can write x to the fifth plus 6x minus 8 over the positive square root of x as x to the fifth over x to the 1/2 plus 6x over x to the 1/2 minus 8x to the 1/2. Now, if we do some algebraic simplification, so for example, this exponent, so here we would subtract the exponents. So here I would have x raised to the 5 minus 1/2. 5 is 10 over 2. 10 over 2 minus 1 over 2 is 9 over 2. So here I get x raised to 9 over 2 when you simplify it. And similarly with the other terms. Here x divided by x to the 1/2. Remember, this is x to the 1. So this will be x to the 1 minus 1/2. 1 minus 1/2 is exactly 1/2 here. And finally, for the last term, I just brought it up and put, with a negative exponent. So what was the point of doing all this? Well, the point now, and there was a point, is that they all look like x raised to the n. And we know the derivative formula for x raised to the n, right? If you very carefully look at the form now, it's important to pay attention. So here, look, variable raised to a number, variable raised to a number, variable raised to a number. So now, yeah, we can take the derivative. So f prime of x means I'm taking the derivative of this function here that I simplified. So I've got this function here now that I want to take the derivative of. So now I'm going to use those properties. The derivative of a sum or difference is the sum or difference of the derivatives, and the derivative of a constant times a function is the same as the constant times the derivative of the function. So here, what you should notice is I've distributed the derivative to each term, and then I've pulled out the constant from the derivative. And so now I just need to calculate the derivative of this part using our power rule. And you should see in here, this is in the form x raised to a number. So for the first one, remember the formula is the derivative of x to the n is n times x raised to the n minus 1. So we bring the exponent down. So here, the 9/2, I brought it down in front. And then from the 9/2 in the exponent, we're going to subtract 1. And 1, you remember, is 2 over 2. So 9 over 2 minus 2 over 2, that's where this 7 over 2 is coming from. And similarly for the second term, x to the 1/2, I bring the 1/2 down, multiply the 6, so I get 6 over 2. And then in the exponent, I subtract 1 from 1/2. 1/2 minus 1 is negative 1/2. For the last term here, the minus 1/2 comes down. There's already a minus there, so minus minus becomes plus, and then 8 times 1/2 looks like 8 over 2. And here, minus 1/2 minus 1, that's like minus 1/2 minus 2 over 2, that gives me minus 3/2. So at this point, we're done with the derivative. The only thing left is to do any obvious simplifications in any obvious algebra. Our rule is to always try and simplify or do any obvious algebra, combine any like terms. So here's 6 divided by 2, I can replace with 3, and 8 divided by 2, I can replace with 4. So here's my derivative, And I think the important things here to remember are, here was rewriting it. That's one big step. And then using the properties of the derivative to break it up, and then finally using the power rule. So there's kind of these 3 steps here of rewriting it, using the rules of the derivative and then doing the actual derivative. For the second derivative, is not much different. It's very similar. I just wanted to basically review. We're now going to take this function and find its derivative for the second derivative. So here, that's what I'm trying to do here now. I say, okay, let's now find the derivative of the previous result that we just got here. And again, I'm going to distribute the derivative to each term and pull the constants out. So here, we pulled out the 9/2 from the derivative, the 9/2, the 3, and the 4. So this property of the derivative is called linearity. So this property right here, where you can distribute the derivative across sums or differences, and you can pull the constant out. It's called linearity. So it's like the word linear with the letters ity attached at the end. And after you take Calc 2 and after you take Calc 3 and after you take differential equations, you'll take a class called matrix methods or linear algebra, and they'll talk about the linearity of the differential operator. And the integral also has this linearity property. You can distribute it across sums and differences, and you can pull constants out. And so we'll talk about all of that more. And so here now, when we do the derivative, I'm using my derivative power rule. Bring the 7/2 down in front. So when I bring the 7/2 in front, I'm multiplying by 9/2. And so now 7 times 9 is 63, 2 times 2 is 4. That's where this is coming from. And from 7/2, we have to subtract 1. So remember, 1 is 2 over 2, 7 over 2 minus 2 over 2 is 5 over 2. So that's where this is coming from, the 5 over 2. For the second term, we copy down the plus 3 and take the derivative of x to the minus 1/2. Here, the minus 1/2 comes down and multiplies to the 3, so I get minus 3/2. And from minus 1/2, if you subtract 1, minus 1/2 minus 2 over 2 is minus 3/2. And finally, for the last term here, I'm bringing down a negative 3/2 in the front and multiplying to 4. So 4 multiplied by negative 3/2. Here, 4 and 2, I can cancel the 2. Minus 2 times 3 is minus 6, and that's where that's coming from. And finally, in the exponent, we have minus 3/2 minus 1 here in this exponent, and that's minus 5/2. It's minus 3/2 minus 2 over 2 is minus 5/2. So quite anticlimactically, here's our second derivative. 6/3 over 4, x to the 5/2 minus 3/2 x to the minus 3/2 minus 6x to the minus 5/2. Right now, it's kind of random. We're not doing anything with these derivatives right now. We're just finding derivatives. That's not the point of calculus. The point of calculus is to do stuff with these derivatives. And so that's what we're building up to. Once we learn our derivative rules, then we can actually use the derivatives to start to analyze functions and to model the real world and to do engineering. So here is actually an application of the derivative. So the question says, find all vertical tangent lines of f of x equal to x to the 1/3. Remember in this class, I said you want to classify the problem as either being a limit problem, a derivative problem, or an integral problem. Here, this is a derivative problem because the vertical tangent line of f of x equal to x to the 1/3, all they're asking us to find is where, to take the derivative and determine where the limit of the derivative blows up to infinity or minus infinity. Basically, we're trying to find the vertical asymptotes of the derivative. So here, I'm just finding a derivative using our power rule. So this is x to the n, where n is 1/3. So I bring down the 1/3, and 1/3 minus 1 is minus 2/3. And here, the minus 2/3, that should really be in the denominator. So I put it downstairs. And so look, the derivative here looks like this. And the function looks like this. So what we're looking for now is a point in the domain of the original function where the derivative might blow up to plus or minus infinity. And this is why I mentioned the domain of the original function. Think about the domain of the derivative versus the domain of the original function, right? The domain of the cube root of x is all reals, but the domain of this derivative here, obviously x cannot be 0. So I'm going to check 0 for whether the derivative has a vertical asymptote. So that'll mean the original function has a vertical tangent. And here, obviously, it is going to be an asymptote because it makes the denominator 0, but it does not make the numerator 0. But to be perfectly accurate in math, we should check it in the limit because the definition involves limits. So here I take the limit, and I take a two-sided limit, and I want you to think about that. I take a two-sided limit as x goes to 0. When I plug it in, I get 1 over 0. I get a number over 0. And the rule is that number over 0 in a one-sided limit is infinity or minus infinity. Here I'm doing a two-sided limit. Why? Well, because if you look at x to the 2/3, what that means is we're taking x and we're squaring it, and then we're taking a cube root. When we take x and square it, that makes it non-negative. So in this case, I don't need to do the one-sided limits because this expression, x to the 2/3, is always greater than or equal to 0. Whether you go from the left or the right, it doesn't matter. X to the 2/3, as a matter of definition, because it's being squared, is always greater than 0, greater than or equal to 0. So here, that's why I'm doing a two-sided limit. Whether you approach it from the left or the right, it's always going to be a positive number over 0, so it's always going to be plus infinity. So yeah, here I just did the two-sided limit, and that's how I get plus infinity here from the two-sided limit. It's number over 0. This is always non-negative, so the limit is plus infinity. So the conclusion here is that the derivative, the slope blows up to infinity at a point in the domain of the original function. So the cube root function has a vertical tangent at x equal to 0. And this is no surprise to us because we've seen it in the graph, right? So here, if I draw a tangent line, so here's a tangent line before the origin. Here's the tangent line, let me try that again. Here's the tangent line after the origin. At the origin, you can see the tangent line is vertical. So yeah, the slope is positive, goes completely to plus infinity, and then comes back from plus infinity and is some positive number, which is, kind of crazy because it goes to infinity and comes back. So yeah, here we're using the derivative to find some geometric feature of the graph. So here, this is a derivative problem where we're using the derivative to do something. And that's what the rest of this course is going to be. Once we establish derivatives, get our derivative formulas down, we'll have a bunch of different applications. Here I wanted to prove that the derivative of sine is cosine. This example is extremely difficult. This is not a type of example you would see in your homework, on a test, or anywhere, okay? This is a difficult example. I didn't want to just give you the formula and tell you to memorize it. I did want to show you the proof. One part of being a math major, and I know not all of you are math majors, but some of you are, part of being a math major is to look at difficult proofs and learn from them. It's like when someone else goes through some kind of experience, we try to get information from their experience, not necessarily go through the experience ourselves. So here, for this example, I'm going to need the two special limits. So the limit of sine of theta over theta as theta goes to 0 is equal to 1, which we proved previously using the squeeze theorem. And this is another special limit that can be proved using the sine of theta over theta equal to 1 result, and trig identities. So it's actually done as an example in the book. But anyway, these results come from squeeze theorem, and so now we're going to use them to find the derivative. And there's one more thing I need is this trig identity, which you may or may not remember from pre-calculus. So in pre-calculus, we have what's called the sum and difference formulas for the sine and cosine function. So this is the sum formula for sine. So, okay, I'm starting with the limit definition. The derivative of sine of x equals the limit of f of x plus h minus f of x over h as h goes to 0, where in this case, f of x is the function sine of x. So f of x plus h looks like this, and f of x looks like this. So now we'll use our identity. We'll use this identity right here, our sum and difference identity, on this expression, the sine of x plus h. So think of a as x and b as h. So sine of x plus h will equal sine x cosine h plus sine h cosine x. And so that's exactly what we have here. Using the identity, we get this. So I've replaced this expression with that longer sum there. And now just a little algebra and we'll be done. And of course, this is the other term that was just hanging around. So now what I want to do is combine all the functions that have a sine x. Put those next. So I'm going to take this minus sine x here. I'm going to take this entire term and move it over here. And this other term, sine h over cosine x, I'll just, I'll have that by itself. And then I'm going to break it up into two fractions. So here I broke it up into two fractions. So it originally was a single fraction. The whole thing was over h. The entire thing was over h with a plus right here. And so there's the sine x that I moved. And so I take the single fraction and break it up into two fractions. And now I'm going to factor out the sine of x is a common term in the first expression. Factor it out, and now we can use the special limits. I told you this was not easy, it's not trivial, and I would never ask you to do this. So, this is tricky, but it's good for our brain, So for this limit, the limit only cares about the variable h. So what does that mean? Sine of x, which does not have an h variable in it, basically acts like a constant. We're just going to copy it down. The limit only cares about, in this case, cosine of h minus 1 over h, because it has the variable h, and sine of h over h. And we can do these limits. As h goes to 0, I'm using this limit right here, this special limit up here for this. So this says the limit of cosine of blah minus 1 over blah as blah goes to 0 is 0. Well, that's what I have here, cosine of blah minus 1 over blah, and blah is going to 0 right here. So this whole piece is going to go to 0. And for this other part, I'm using the other special limit. So I'm using this limit right here. Again, I have sine of blah over blah, and the blah is going to 0. So that limit, this should go to 1 by the special limit. And the sine and the cosine we just copy down because they don't have the letter h in it, and the limit only cares about anything with the letter h in it. So you get the limit is equal to sine times 0 plus cosine times 1, or just cosine. That is to say, the derivative of sine is cosine. And so that's a new rule that we should memorize. And using a similar technique, we can show the derivative of cosine is minus sine. So here we use the sum and difference formula for the cosine of x plus h. And I'll let you think about that if you want to. So at the end of the day, what you absolutely need to know from this slide are these two pieces of information. You need to know the derivative of sine is cosine, and you need to know the derivative of cosine is negative sine. You don't need to know this proof. But if you can follow along, if the steps can make sense to you, that's perfect. That's ideal. That's what I'm hoping. So let me define the normal line, and then we'll see how much time we have. I might stop here. So just like we have a tangent line, there's a thing called a normal line. And I know the word is a little weird, the use of the phrase normal. I'll try and figure out exactly why they call it that. But the normal line to the curve y equal to f of x at the fixed point x equal to a, just like we define the tangent line to a curve at a fixed point. The normal line is the line that goes through the point a comma f of a and is perpendicular to the tangent line at a comma f of a. So we know that the slope of the tangent line is f prime of a. So any line that's perpendicular to that will have slope -1 over f prime of a, because lines that are perpendicular, their slopes are negative reciprocals of each other. So here is the equation of the normal line. So here I wrote it this way first, just in more like point slope form, f of a plus here's the slope of the normal line, m for slope sub n for normal line times x minus a. And to be perpendicular to the slope of the tangent line, the slope of the tangent line is f prime of a, the slope would have to be -1 over f prime of a. So at the end of the day, this is our equation for the slope of a normal line. So let me do a quick example. And so here, this is also an example of how do we do the derivative. Okay, so here it says find the equation of the normal line to y equal to quantity 1 plus 2x squared at the point x equal to 1. So I'm looking at this problem, I'm going, okay, it's not a limit problem, but it is a derivative problem. I'm classifying it. And here, for the equation of the normal line, we want this equation. Now look, the number a we know a. A is the number 1. F of a I can find. Sorry, not f prime of a, I meant to say f of a here. F of a I can find, because I know the function f of x. I just need to plug in the number a, which is 1. The only thing I don't know is what's the derivative at a. This is the thing I need to figure out. That's why I say this is really a derivative problem. Once I find the derivative, I just plug everything in and we're in business. So let's try and find the derivative. The first thing I notice is this is not a function I have a derivative formula for. If you give me a function that looks like this, x to the n, I know the derivative of x to the n. If you give me cosine or sine, I know those derivatives. I don't know the derivative of quantity 1 plus 2x squared, okay? So later on, we'll learn a rule called the chain rule, which is probably the best way to do this. But right now, we don't know the chain rule, but we can still do the problem. That's important to remember. We can still do the problem. So here, if I FOIL out 1 plus 2x squared, then each of these terms I know how to find the derivative of. I know the derivative of 1 is 0. I can find the derivative of 4 times x. I can find the derivative of the 4x squared. Okay, so now what I'm going to do, once I FOILed it out, I'm now going to take the derivative of this expression. The derivative of 1 will be 0. The derivative of 4x, so 4 I copy down, and now I want you to think about the derivative of x here. X is actually x raised to the first power. So now if I do a derivative, I want to bring this number 1 down, right? So here, I bring the 1 down, and then this is x to the 1 minus 1. That's x to the 0, which is 1. The derivative of x by itself is just 1. So here this will be 4 times 1 plus 4 times the derivative of x squared. I just bring the 2 down, x raised to the 2 minus 1. And here 4 times 2 is going to be 8. So I'm looking for 4 plus 8x as the derivative, right? The derivative of 1 is 0. Derivative of 4x is 4. The derivative of 4x squared is 8x. And now this is f prime of a. I want to plug in the a, which in this case is 1, into the derivative. And so when I do that, I get, plug in a 1 for the x, 4 plus 8 is 12. I get f prime of 1 is 12. So this is the slope of the tangent line. So the perpendicular to this would be negative 1/12. So now here's my formula for the equation of the normal line. I found f of 1. Whoops. If you plug in 1 right here, so here if I plug in 1 right into the original function, so I get 1 plus 2 is 3 squared is 9. The negative 1/12 is the slope of the perpendicular line. That's coming from the 12. And so then I just did some algebra here. So you remember 9 is the same as 108 over 12. You wouldn't have to combine it. I just did it just because I felt like it. And then don't forget to distribute the minus sign. So mathematicians have feelings too. So here's the graph. This line right here is the tangent line here that I've drawn right here. That's the tangent line. And then you can see the other line here that's perpendicular. This is our so-called normal line right here. This is the normal line. And for motion in 2 dimensions, forces along the tangential direction and forces along the normal line basically tell us everything that's happening. So when you look at this picture, I want you to think about it as you're looking from above at someone that's on a skateboard, okay? I've never been on a skateboard in my life and I never will be, but from what I understand, you stand on the skateboard and you kick your feet in the tangential direction. That's what makes the skateboard move forward, when you kick your feet and you've got force in the tangential direction. And now you're on your skateboard and you want to turn right or left. From what I understand, if you want to turn left on your skateboard, you lean left. And that gives you a force in the normal direction that causes the skateboard to lean left, to move left. And similarly, if you want to go right, you lean right. That gives you a force in the normal direction, to the right, and that causes a right turn. So all motion in 2 dimensions can be described by combinations of forces in the tangential direction and in the normal direction. Okay, and we'll extend this in Calc 3. We extend this to 3-dimensional. We'll find all the forces that account for how an object moves in 3 dimensions in space. And so if you're trying to orient a satellite or trying to, fly a plane or whatever, those forces become very pertinent. And this theory is still very pertinent for computer graphics and stuff like that, analysis, low dimensional analysis. This is all very useful stuff. All right, folks, I'm going to stop at this slide. I'll continue with the last slide next lecture.